to x, right? Which will be the hyperplane lying above the separating hyperplane, which will be the half space lying above the separating hyperplane, right? And the set of all x's to which y is strictly preferred. So set of all consumption bundles which lie below that hyperplane, right? Okay, which lie below that hyperplane. Sure? Is it clear? Okay. Now, Pakka? Now tell me one thing. Will these two half spaces be closed or open? Open half spaces. Why would those half spaces be open? Because they're strictly less than or strictly greater than. Right? So the half spaces will not contain their boundaries. Now why is this theorem beautiful? Because it says for any consumption bundle x and y, any consumption bundle, there exists an indifference curve passing through that consumption bundle. The first thing that it says is for any consumption bundle, there is an indifference curve passing through that consumption bundle. That's the first thing that it proves. So we know that indifference curves exist. Why? Because of the separating hyperplane theorem. Right? Otherwise we have no idea that indifference curves would exist. It was all a mental concept. You know, formally, mathematically, indifference curves will necessarily exist as mathematical objects. Because when we take derivatives of indifference curve and all that, we know that mathematically they have to exist. Huh? So they have to exist because of the separating hyperplane theorem. The set of all, okay. Now let me ask you a question. Okay. So set of all consumption bundles, right? Below the hyperplane and above the hyperplane will be open sets. Okay? Right? Okay. Now, we have next idea that of the supporting hyperplane. Please learn to distinguish the separating hyperplane and the supporting hyperplane. Separating hyperplane is clear? And through every consumption bundle there exists an indifference curve which will pass and divide the two spaces into, divide the set of consumption bundles into two open half spaces. Absolutely crystal clear? Yes. Through every point there pass an indifference curve which will divide the set of consumption bundles into two open half spaces. In R2, R3, whatever. Yeah, even if the function from R3 to R2 or whatever, right? For example, for production functions also, so what it beautifully says is, through every combination of factor inputs, there exists an isopoint. Right? Okay, there exists an isopoint. Okay? Right. Okay. Now, the supporting hyperplane. Supporting hyperplane is why indifference is crucial to the idea why indifference curves are convex to the origin. Okay, what is the assumption that we make? This means for all. For all x belongs to C. This triangle means for all. Okay, for all x belongs to C. Okay, so what is the difference? So the difference is, now I made the closed subspaces closed. Either h of x less than or equal to b or h of x greater than or equal to b. So what we are saying is, if you have a set of indifference, if you have a set of conjunction bundles, okay, fine. So think of a set of conjunction bundles and think of some y. There will always exist a y, okay, so that conjunction bundles below y will be at least as good as y, or weakly preferred, or y will be at least as good as these conjunction bundles, right? Okay, sure. Okay, now tell me, so what is a supporting hyperplane really? A supporting hyperplane is nothing but the boundary of a set. It's a set of all x's. Now, in the last class I talked to Professor Raju and she said that she has talked to you about convex preferences. So what are convex preferences? You know, upper contour sets and all that. Yeah? You learned the assumption of convex preferences. What are convex preferences? What is the upper contour set? You remember the upper contour set? If you think of any x, then the set of conjunction bundles which are at least as good as x is the upper contour set of x. You learned this definition? If you think of any conjunction bundle x, then the set of conjunction bundles which are at least as good as x is the upper contour set of x. Right? Okay? Then the next assumption that we make is the upper contour set is convex. The upper contour set. The upper contour set, किया था क्लास में? अच्छा, convex preferences, convexity of preferences. What do you mean by convexity of preferences? We say preference is a convex if you take any x, the set of all conjunction bundles which are at least as good as x as is convex. Right? What does this statement mean? Take the set of all conjunction bundles which are at least as good as x, and when I say that the set of at least all the conjunction bundles which are at least as good as x is convex, what does it intuitively mean?
If we take a set of all conjunction bundles and name it S, and we take a conjunction bundle X within the set S, and we take another conjunction bundle Y which is at least as good as X, and that is also within the set S, then if we draw a line which joins both the sets, it lies exactly within S.
Yeah. So, but what is the property of S? S is the property that all conjunction bundles in S are at least are preferred to the conjunction bundle X. That is the definition. So it says if x1 and y1 are two conjunction bundles which are preferred to x, any linear combination of x1 and y1 will also be preferred to x. That is the convexity of preferences idea. Right? That is the convexity of preferences idea, which says that if x1 is at least as good as x and y1 is at least as good as x, then any linear combination of x1 and y1 will also be at least as good as x. Right? Everybody gets this idea? This you have talked about in class, haven't you? Yeah? If you take any two conjunction bundles at least as good as x, then their linear combination will also be at least as good as x is the idea of convex preferences. Right? Okay. Another way of putting it is to say that the set of all conjunction bundles which are at least as good as x if we give the name the upper contour set of X. So what is the upper contour set of X? Set of all consumption bundles which are at least as good as X. And a simple way of saying this is that the upper contour set is convex. The upper contour set is convex. Okay? The upper contour set. The upper CONTOUR, the upper contour set is convex. The upper contour set is a very simple idea. Set of all consumption bundles which are at least as good as X. And when I say the upper contour set is convex, I say that if any two consumption bundles are at least as good as X, then the linear combination of these two consumption bundles must also be at least as good as X. Yeah, that is what is meant by the upper contour set being convex. Okay. Now, so think of the upper contour set being convex. We have a convex set in S R. So think of x1, x2 and all linear combination of x1, x2, right? Which are at least, so think of this. So think of, say, y and x. Think of some consumption bundle which I call x star. Think of the set of all consumption bundles which are at least as good as x star. Which is the upper contour set? I require that upper contour set to be convex. Right? So I am looking at some combinations like this. Yeah? Right, because this is a point in the upper contour set, this is a point of linear combination line in the upper contour set. So the upper contour set will be all these. Yeah? Right? Now what is the supporting hyperplane here? So this is C, right? Suppose keep this upper contour set as C. It's a convex, non-anti-convex set. Right? What do you mean by the supporting hyperplane of this?
The space above S which contains S and the space below S which also contains S.
Those are half spaces, not the hyperplane. Think of the supporting. What is supporting? There is supporting hyperplane Hx of B, set of all points which are mapped into the same point B, such that y is in the hyperplane, right? For y not belonging to C. So, right, y is not belonging to C, and of all of C to entirely on one of the two closed half spaces associated with the hyperplane, right? Associated with the hyperplane, right? So basically, what you can think of is either for all x, h of x is less than or equal to b, or h of x is greater than or equal to b, right? So we can think of, so it says that there will exist, if you think of some y, for any y, there will exist consumption bundles which will have the property that the utility of these consumption bundles is at least as much as the utility of y. There is consumption bundles, right? Okay, right. So this gives you the supporting. This is the upper contour set. Now the point is, do you think the upper contour set is somehow, okay, the boundary of the upper contour set has something to do with the separating hyperplanes and indifference curves? This is the boundary of the upper contour set. The upper contour set here is, of course, right, less than or equal to, right? So it must be a closed set because we are using the weak references. So there will be some conjunctive bundles y which are at least as good as, so which satisfy this, right? So what can you think of that? What can you conceptualize this boundary? We are talking of closed half spaces. There is two closed half spaces, okay, associated with the hyperplane. Either x belongs to C, such that hx is less than or equal to b, or hx greater than or equal to b. So think of this in the next class, because that's what will tell you why difference curves are convex to the origin, right? And what do you think of hyperplane and support? You can do some research work on your own. All of you have got access to Google now, right? I will leave you with these notes. Okay, the one of those set of notes you already have, open and closed sets, which I need to deal with a little bit more, right? Because we need to prove just one logical thing. But apart from that, this you will have. How much more time do we have? right? So will you be able to, so just think of this. I'll leave you at this point. What does all this have to do with indifference curves? And the argument that indifference curves are convex to the origin. And can we do away with that assumption of diminishing marginal utility and all that? And think in terms of this structure. I've left you with the ideas. Right? In the next class I'll talk to you, I'll ask some of you this question. About what do you think this works, right? So do some research on your own. And then next class is tomorrow, right? Yeah, so go home, find out things on your own, and let's talk about this. Right? So then you'll get a sense of why this is important for economics. Yeah? Okay.